In this module, we focus on the second type of analysis of associations that involves correlation coefficients. If you recall, when analyzing associations between variables, the type of analysis depends on the types of variables you have in the analysis. In this module, we focus on the case where both variables are metric, that is, use interval or ratio scales. While there are different types of correlation coefficients that can be calculated, we will focus on the Pearson correlation coefficient. We would calculate this when analyzing the association between two metric variables. For example, when we want to see if advertising expenditure is associated with sales revenue. Let's review the meaning and interpretation of correlation coefficients briefly. A correlation describes how variables move together. If both move in the same direction, then the correlation is positive. In other words, if one increases when the other increases, or if it decreases when the other decreases, this is a case of positive correlation. For example, advertising and sales will usually be positively correlated. The value of the coefficient will lie between 0 and +1 in this case. If both move in opposite directions, then they are negatively correlated. That is, one increases while the other decreases. For example, price and quantity demanded will usually be negatively correlated. In this case, the value of the coefficient will lie between -1 and 0. If the change in one variable does not depend on how the other changes, that is, they are independent of each other, then they are uncorrelated, or the correlation equals 0. While correlation coefficients are useful summary measures of association in many cases, it is important to remember that they can only describe the extent to which the relationship is linear, that is, the extent to which the data points on a graph lie along a straight line. Let's take some examples to see what this means. In this example, showing the relationship between sales and advertising, the correlation will be positive because as advertising increases, so does sales. This shows the plot of sales with the number of competitors. As the number of competitors increases, sales decrease. This is an example of a negative correlation. What do you think the correlation coefficient will be for these data? It will be 0 or close to it. It's obvious that there is a relationship between the variables x and y, but it is not a straight line or linear relationship, and the poor correlation coefficient just throws up its hands and says, forget about it, I cannot figure this one out. So this is why it's important to remember that a correlation coefficient cannot describe certain types of relationships. Before drawing any conclusions from the value of the correlation coefficient, we must conduct a test to see if the correlation is statistically significant. The null hypothesis for this test is that the true correlation is 0. The alternative is that it is not 0. Note that this is a two-tailed test because the hypothesis can be rejected if the correlation is either positive or negative. The test statistic is calculated using this formula, where R is the correlation in the sample and N is the sample size. This is distributed as a t-statistic with n-2 degrees of freedom. As always, we use the decision rule that if the test statistic is greater than the critical value, we reject the null hypothesis. Of course, with SPSS, we need not do any calculations or look up a critical value in a table. We simply use the alternative decision rule. That is, if the p-value is less than alpha, we reject the null. Here's what you get from SPSS if you run a bivariate correlation analysis. This example is from the National Insurance Company dataset. All the variables in the analysis are shown in the rows and in the columns. Each cell shows the correlation of the corresponding row variable with the column variable. So the first thing to notice is that the diagonal cells show the correlation of each variable with itself. And since this is always going to be 1, that is, perfect positive correlation, these cells can be ignored. Second, notice that this is a symmetric matrix. That is, the cells above the diagonal are the same as below the diagonal. So you can ignore one or the other set of cells. Let's focus on the below diagonal cells. Each cell has 3 entries. The first is the value of the correlation coefficient, the second is the p-value of the test for it, and the third is the sample size. Looking at the highlighted entries in the second row first column, we can see that the correlation between the row and column variables is 0.777, which is pretty high. The p-value for the test for the correlation is 0.000, which means that it is so small it is not going to show up even with 3 decimal places. Since our decision rule is that when the p-value is less than alpha, we reject the hypothesis, in this case we obviously have to reject the hypothesis, no matter how small an alpha value we choose. The hypothesis we are rejecting is that the true correlation is zero, so clearly the variables are strongly positively correlated. Now what does this mean? It means that the responses to the two scales, when National promises to do something, it does so, and how would you rate the overall quality of service provided by National, are highly positively correlated. That is, the variables move together very closely in the same direction. Someone who gives a high score on the first variable will also give a high score on the second. The implication for National is that their perceptions of overall quality are driven to some extent by their ability to fulfill their promises. And that's pretty much all there is to correlation.